Hello everyone, welcome to Saimedha Koti, Hyderabad. In this session, I would like to discuss about electrical machine question which were asked in the TS Genco exam. So let's start from the question number 1. The question 1 is belongs to the DC machine. So question 1 is a 250 volts DC shunt motor takes a current of 41 amps. The runs at 800 RPM on full load. The armature and field resistance are 0.2 ohms and 250 ohms respectively. During stalling of the motor, the resistance of the 2 ohm is placed in series with the armature. Then the ratio of stalling torque to the full load torque is around option 1 1.42, option 2 2.84 and option 3 1.25 and option 4 1.13. So given the 250 volts DC shunt motor, so now this we know that torque is directly proportional to the flux and armature current. So in the DC shunt motor, flux is a constant. Okay, this flux is constant. So therefore the torque is directly proportional to the armature current. So now we required ratio of the stalling torque to the full load torque. So how do we get? So this one is stalling torque. The torque stalling divided by the full load torque of the motor TFL, so is equal to current in the armature current under stalling condition. So this one is the stalling condition divided by armature current under the full loaded condition. So if you find this ratio, that we required armature current under stalling condition and armature current under the full loaded condition. So how do we get these two? What is the mean by stalling torque? Stalling torque means torque produced by the motor when the speed reduced to the zero, when speed of the motor falls to the zero. So that means when the speed is equal to zero, then what will happen? The back EMF of the motor is equal to the zero. So when back EMF is equal to zero, armature current is equal to V by the V minus IRA, V by RA. But during stalling there is a resistance 2 ohm is inserted. So therefore RA plus RE external resistance, it is equal to 250 volts. So divided by 0.2. So 0.2 plus the 2 ohms. This value is equal to the 250 divided by 2.2. So this one is the armature current under full loaded condition. Sorry, armature current under stalling condition. Now we required armature current under full loaded condition. So DC shunt motor current, armature current, full load current is equal to IA is equal to total current minus. So this one is a shunt field current. So this value is equal to I minus the V by RSH value. So here I is equal to the 41 minus and this V by RSH. Okay, V is the 250 volts, RS is the 250 ohms. So now it is equal to 40 amps. Okay, this is the armature current under the full loaded condition. So now just substitute these two. Okay, here first let us armature current we know 40 amps. Okay, this one is the 2.2 amp. So 250 divided by 2.2. Okay, 2 amps. And next let us find out this ratio, stalling torque divided by the full load torque of the motor. So T full load is equal to, so stalling current is equal to 250 the divided by 2.2. Okay, this 2.2. So full load current is equal to 40. So by simplification, so this is equal to 250, so divided by 2.2 into 40. So now by solving here we will get, okay, this one is the 2.84. So just verify. So with the calculators, then the 2.84 so is right answer for this question. So 2.84 is the right answer, the ratio of the stalling torque to the full load torque. Okay, and next one, let us solve the question number 42. The question is, the self excited DC generator fails to build up of the voltage at no load, identify the correct reasons from the following. So, this options of the residual magnetism, statement number 1. Statement number 2 is field resistance is less than the critical field resistance. The statement number 3, speed of the armature is more than the critical speed, and field resistance is more than the critical resistance. The speed of the armature is less than the critical speed. Option 1, 2 and 3 only. Option 2, so 1, 2 and 4 only. Option 3, 1, 4 and 5 only. 1, 2 and the 5 only. So we know that what are the conditions that required to build up of voltage in the self-excited DC generators. The condition number 1, the field poles have some residual flux and field polarities are properly connected to the armature winding terminals in such a way that initial field flux aid the existing residual flux. And condition number 3 is a speed of the generator must be above its critical speed, and condition number 4 is the field resistance of the generator must be below the critical field resistance. So these are the 4 conditions are required to build up of voltage in the self-excited the DC generators. Now let us verify these conditions here. So identify the correct reasons. So here fails to build up of the voltage. So what is the reason to fail the build up of voltage in the self-excited DC generator? See the statement number 1, absence of the residual magnetism. The field poles don't have the residual flux. That means there is a generator fails to build up of voltage. So this is a correct statement. And field resistance is less than the critical field resistance. Now if field resistance is more than the critical field resistance, the generator fails to build up a voltage. Okay, now this statement is also this one is field resistance is less than the critical field resistance. This is the wrong statement. And speed of the armature is more than the critical speed. So now speed is a more than the critical speed point of view. Always to build up of voltage in the self-excited DC generators, the speed of the generator must be above the critical speed. So this one is the correct statement. And field resistance is more than the critical field resistance, critical field resistance value. So now this one is generator fails to build up of voltage, and speed of the generator, the field resistance is more than the critical field resistance. If field resistance is more than critical field resistance, generator fails to build up of voltage. Okay, this one is the correct statement. And speed of the armature is less than the critical field resistance. So now these two are, see this one is the correct statement, and speed of the generators is a less than the critical field resistance. Now this is also the wrong statement point. So now we required generate fail, what are the reasons? Suppose speed must be less than the critical speed, the one of the reason, and the resistance of the field winding is greater than the resistance of the critical resistance. So now just verify these two conditions. So now first one is so field resistance is less than the critical field resistance. This condition is required to build up of voltage. So these two conditions, and speed of the armature is more than the critical speed. This is also required condition. But speed of the armature is more than the critical speeds, resistance of the more than critical speed condition. So that's why these two reasons, okay, that means 1 and 4 are this field resistance more than and speed is the less than. So these three, one condition statement is one of the reason, the fourth is also reason, and fifth is also reason to build up, to generator fails to build up of voltage. And next one, let us solve the question number, okay, this question number 46. A short shunt DC compound generator supplies the load current of 100 amps at 250 volts generated as the following shunt field resistance: 130 ohms, armature resistance 0.1 ohm, series field resistance is 0.1. Find the EMF generated. The brush voltage drop is 1 volts per brushes. So now this value is a 270.2, 160.2 volts, 262.2 volts, and this one is the 272.2 volts. Now in the short shunt compound generators, so this one is the field winding, series field winding, and this one is armature, and shunt field winding is connected across the armature winding terminals only, and this one is a load is connected across combination of series field winding and the shunt field winding. So we required generated voltage EZ. So this one is armature current, and this is the shunt field current, and this current is the series field current. It is also equal to the load current. So now first one, let us calculate this shunt field current ISH here. ISH is equal to VT plus IA IL RSC divided by RSH value. So this RSH. Now VT is equal to, so what is the terminal voltage? So 250 volts. The plus IL is equal to the 100, the RSC is equal to 0.1, and RSH is equal to shunt field resistance. So this shunt field resistance also 130 volts. Now this is equal to 0.260 by 130, so equal to the 2 amps. Shunt field current is equal to the 2. So if it is shunt field current is, and this is equal to 2 amps, then armature current IA is equal to, so this IL is a 100, okay, plus, okay, this one is IL, okay, plus ISH. So it is equal to 100 plus 2, okay, it is equal to 102 amps. So armature current is 102 amps. And next one, we required generated voltage. How do we get the generated voltage? The EZ is equal to VT plus, okay, IA RA, the plus ISC, okay, ISC RSC, the plus some amount of the brush drop, 1 volt per brush, okay, you can say that VBD, and this value you can write VT plus IA, the RA plus ISC into RL, okay, plus some amount of the brush drop. So now substitute here all the values in this equation. So let us substitute first one. So voltage is equal to 250, the plus IA is equal to, armature current is 102 into 0.1, the plus ISC series field current is equal to load current only. So that is RSC values. So this one is load current, RSC values 100 into 0.1. Suppose how much amount of the brush voltage? 1 volt per brush means generally 2 brushes are there, 2 volts. So by solving this, you will get the 272.2 volts is the right answer for this question. So 272.2 volts, okay, is the right answer. So for this question, okay. And next one, let us solve question number 43. So this question belongs to the transformer. So let us solve the question number 43. 11,200 upon 100 kVA single phase 2 winding transformer is to be used as an auto transformer by connecting the 2 windings in the series. Which of the following are not possible values? Okay, this point is a very important. Which of the following are not possible values of voltage ratios and kVA output of the auto transformer? So auto transformer ratings, first one, given voltage rating here, 2 winding transformer. So this 2 winding transformer is there. So 2 winding transformer rating, so first one, so this is a 11,000, okay, the 11,000 upon 2,200 volts, okay, and let us assume it is a EHV the divided by ELV values, okay, EHV by the ELV. So this one is the 2 winding transformer rated. And first case one, the case one is assume as case one is a the series additive polarity connection, okay, here additive the polarity connection point of view. So assume that the auto transformer is obtained from the 2 winding transformer by that series additive polarity nature. So in the series additive polarity nature means, for example, so if applied voltage V1 is equal to 11,000 volts, okay, 11,000, and V2 will become, so this one V2 will become EHV plus, okay, here EHV plus ELV value. So this value is equal, if applied voltage is equal to 1100, this will become, so this one is the 11,000 plus 2,200, so that is equal to 13,200 volts. Okay, we got the V1 by V2. And what is the voltage rating? So V1 by V2 is equal to the transformation ratio, the K is equal to the low voltage by, so K value, see this one K, so where K is equal to transformation ratio, so that is V low voltage with a VLV, so that is low voltage of auto transformer, the divided by high voltage of auto transformer. What is the low voltage in this case? V1 is a low voltage 11,000, so divided by 13,200. Okay, this 11,000. Now let us find out KVA rating of auto transformer. KVA rating of auto transformer is equal to 1 by 1 minus K times of the KVA rating of, okay, 2 winding transformer. Now simplify this. Okay, here 1 and 1 minus K value is equal to, so this is the 11,000 divided by 13,200. So into K is equal to 10 kVA is there. So 10 kVA, that 10 kVA. So now simplify. So this is equal to 13,200 divided by, so 2,200. So now simplify, multiplied by, so it is equal to 10 kVA. So now it is equal to, that 0 0 is cancelled out. Okay, 11. So now by solving this we will get, okay, 120. Okay, this one is that 10 and 120 kVA. Let us simplify. This one is 100 kVA, not 10, so that it is equal to 600 kVA is there. So now voltage rating. So this one is the rating of the rating. So 13,200 by, so it is a 11,000 by 13,000, this one. So it is a rating of the transformer, so that we can eliminate this option. And next one more possibility, let us check. Okay, possibility here. Suppose if the applied voltage is equal to this one is the 2,200, so V2 will become, so this V2 is a VHV plus VLV, so that the VHV the 11,000, the plus 2,200, so this is equal to 13,200. So where K is equal to 11 low voltage of auto transformer divided by high voltage of auto transformer. Now what is the KVA rating of, okay, this KVA rating is equal to KVA rating of auto transformer. So it is equal to 1 minus K. K is equal to 2,200. So divided by 13,200. So multiplied by 100 kVA. So now simplify this. So now it is equal to, so 1,200. So divided by, so this one is, okay, 11. So 11,000. So now simplify. So 13,000 divided by 100. So now it is equal to, so let us verify what is the answer for this question. So it is equal to 120 kVA. So now this is a 120 kVA. So 120 kVA. So this is that kVA rating. So this is also kVA rating of auto transformer. But we required which one is not kVA rating. So let us take the case 2 also. How to get the case 2? So simply here just verify. So here series subtract, case 2 is the series subtractive polarity connection. Series the subtractive polarities. So in the series subtractive polarity connection, so if V1 is equal to, so this one is a V1, so it is equal to 11,000. So 11,000. So now then, so this one is, and V2 will become the 13,000. Okay, this one is a minus, so 11,000. So it is equal to, so 13,000 minus 11,000. So this also we can get. So this is also possible. So here 120 kVA, but this is not possible. So that option, the 2. So why? Because it is at 2,200 volts. So this kVA rating also possible by using series subtractive polarity, but fourth option is not possible, and option 4 is correct for this question. So like this we can eliminate the options. First find out series additive polarity nature, then verify series subtractive, then final one is will get fourth option is the right. So for this question. And next one, question number 44. Which of the following statements are not correct? The not correct, this point is a very important here. The which of the statements are not correct? So now it is this one, delta star connected 3-phase transformer is used in the beginning end of the HV transmission system. The delta star transformer. So delta star at same voltage rating, that this one is in the delta star transformer V2L is equal to, so this V2L is equal to root 3 times of V by, so root 3 times of, that means delta star transformer produce the highest secondary terminal voltage among all 3-phase transformer connection at same voltage rating and turns ratio. So it is best suitable at the beginning end of the HV transmission lines. So that this is the correct statement. It is correct statement. It is not wrong. It is correct statement. And next, coming to the statement number 2, open delta connection is not possible with a star-star connected 3-phase transformer. So it is wrong statement. Why? Because the open delta connection is not possible, right? So that means open delta connection is possible with delta 3-phase, not possible with the star. This is also, it is the correct statement. Okay, this one is also correct statement. And star delta connection is used in the 3-phase the distribution transformer. Actually, it is a wrong statement. Why? Because it is wrong statement. So why? Because that is a delta star transformer is used in the distribution system, because the secondary star connection provide the neutral point, so due to which you can supply the power to the single phase loads. So that's why it is the wrong statement. Oscillatory neutral problems are not possible present in the star-star connected 3-phase transformer. So this oscillatory neutral problem is present in the star-star 3-phase transformer. That's why we can use the tertiary winding to stabilize the neutral point. So this is also, it is wrong statement. So now what are the wrong statements are required? So that is 3 and 4 options. The 3 and 4 statements are wrong. So that option 3 is a correct. So pick the wrong statement. Okay, this not correct statement. And next, question number 45. The question number 45 also belongs to the transformer. A 10 ohm resistor load is to be impedance matched by the transformer to measure the source of the 6250 ohms, the internal resistance ratio of the primary to the secondary side. So now primary is to the secondary side of the transformer. Option 1 10, option 2 15, option 3 the 20, option 4 is at 25. So now we know that this R2 dash is equal to R2 by K square. Now R2 dash is equal to internal resistance is 6250, where load resistance is equal to the 10 ohms. So by K square. So now simplify this. Okay, here the K square is equal to 10 by the 60, the 6250. So where K is equal to under root of 1 by the 625. So therefore K is equal to 1 by 25. So it is always, K is a transformation ratio N2 by N1, but we required the ratio of N1 by N2. So therefore N1 by N2 is equal to 25. So answer for this question 25 is the right answer. Option 4 is correct. And next one, let us solve the question number question number 51. A 3-phase transformer bank consisting of the 3-phase transformer used to the step down voltage of the phase, the 600 volts transmission line. If the primary line current is 20 amps, the output kVA of the star delta transformer connection, if the turns ratio is 12. So these are the options. Turns ratio means it is denoted by A. So where V2L is equal to, in the star delta 3-phase transformer, so the given transformer is a star, this is the star delta 3-phase transformer. V2L is equal to, so V by root 3 A times, this is equal to 6600 divided by root 3 into multiplied by 12, and I2L is equal to, so this star delta root 3 times of AI. So therefore root 3 into 12 in multiplied by 20. So this one is the 20 amps. Now here kVA rating of 3-phase transformer, kVA rating of any 3-phase transformer. This any 3-phase transformer is equal to the root 3 times of V2L into I2L. So here root 3 into V2L is equal to, what is the value of V2L? 6600 divided by root 3 into 12. and this I2L is equal to the root 3 into 12 multiplied by 20. So, these 2 will be cancelled out. So, now this is equal to root 3 into 132 the kVA, okay, kilovolt amperes. So, this one is a 130 into root 3, that is option 1 is correct for this question. And next one, question number 47. This question belongs to the synchronous machine. Identify the incorrect statement. Here also this point is a very important, incorrect statement among the following. So, in round rotor synchronous motor, the reactive power is maximum at a load angle of the 90 degrees. So, actually reactive power is maximum at a load angle of the 0. So, that is why it is the wrong statement. So, this one is the wrong statement. We required the wrong statements only, incorrect statements. Damper winding is provided in the polyphase synchronous motor in order to provide the starting torque. So, this one is correct statement. So, function of the damper winding, so here it is also starting purpose and also reduce the hunting in the machine. In slip test of the salient pole synchronous machine, the EMF induced in the field winding is 0 for. So, field winding is not 0, this one is the wrong statement. And next one, synchronous condenser and over excited synchronous motor. Over excited synchronous motor, the driving the mechanical loads. Actually synchronous condenser means over excited synchronous motor without any mechanical load is known as the synchronous condenser. So, that is why this statement is a wrong statement. So, now what are the wrong statement? 1, 3 and 4. So, 1, 3 and 4 are the wrong statements for this question. 1, 3 and the 4 statements are the wrong and second statement is correct for this question. Okay. And next one, question number 49. The with visual notations of the following phasor corresponding to under excited alternator, under excited synchronous motor, over excited synchronous alternator, over excited synchronous motors. Now see this, by seeing this diagram, just assume, so VT is a reference here. Okay, I am taking this one is the VT is the reference. So VT leads the here this armature current. So this current is, so this one is current IA. So IA leads this one is the terminal voltage by angle. But which type of power factor? So definitely it is the leading power factors. Okay, leading power factors point of view. So leading power factor means, and here leading power factor, in case one more point of view, see this one. So this wave, this vector, so excitation EMF vector. So in generator, okay, this one is in the generator, always excitation EMF the leads the terminal voltage. Okay, excitation EMF is the leading by some angle. Okay, this one. So that means this diagram is for so alternator point of view. So where are the motors? These two options are wrong. So we can eliminate the two options. But so we required over excited or under excited. How do we answer this one? So under excited synchronous generator absorbs the reactive power at leading power factors. So given already we know the power factor, nature of the power factors. So under excited synchronous generator absorb the reactive power from the bus bar. So to at leading power factor to maintain air gap flux constant. So that answer for this question, option 1 is correct. No need to draw the phasor diagram once again. Just verify what is the nature here. Current leads the terminal voltage. So that leading power factor. Excitation leads the this terminal voltage. This diagram is for generators. So leading power factor and generator. So definitely it is a under excited. The synchronous generators are under excited alternators. Option 1 is the correct. And next one, let us solve the question number 48. This question belongs to the concept of induction machine. The time period of the rotor current of 3-phase 4-pole 50Hz induction motor is 200 milliseconds. Then speed of the motor is, and 3-phase 4-pole 50Hz induction motors. Let us find initially synchronous speed. Ns is equal to 120 So this 120 F by P. So now this is equal to 120 into 50H, number of poles is equal to 4. So that it is a 1500 RPM. So this is the synchronous speed. But we given that here the rotor time period of the rotor current, and that means okay, this one is the TR is equal to the 200 milliseconds. But what about FR? FR is equal to 1 by time period of the rotor current. So 1 by 200 the millisecond 10 to the power of minus 3. So therefore 1000 divided by 200, so it is equal to the 5 the hertz. So we got the rotor frequency. Now the slip is equal to S value. We know that FR is equal to the F into S. So the FR is equal to S into F. So that by FR is equal to the 5 divided by 50. So 5 divided by 50 means 0.1, 1 by 10. So now this one is equal to 0.1. So now we require this N is equal to the Ns into 1 minus S. The Ns is the 1500 RPM. So 1500, and this one is 1 minus 0.1. So it is a 14 the 25, is it correct? So this one is the N is equal to, so 1350 RPM, 0.1, just verify. Yeah, 1350 RPM. So after getting 1350 RPM, but we required slip speed. So that slip speed is equal to, how do we get the slip speed? The slip speed is equal to the Ns minus okay, N. So now this is equal to 1500 minus 1350 is equal to 150 RPM. So answer is 150 RPM is correct. So this option 1 is correct for this question. And next one, let us solve question number 50. The question is, which of the following statements are correct? A question that the correct statements are required. Which of the statements are correct? So these correct statements, respect to the 3-phase induction machine. Cogging and crawling are less prominent in the slip ring induction machine. Yes. Why? Because slip ring induction motor has high starting torque as compared to the squirrel cage induction motor. The mostly the cogging and crawling effect occurs in the squirrel cage induction motors. So now this one is the wrong statement, the wrong one. And induction harmonic torque can be reduced by skewing. Yes, harmonic torque can be reduced by the skewing. This one is the correct statement. And synchronous harmonic torque can be avoided by proper combination of the stator teeth and the rotor teeth. So when rotor slots are equal to the stator teeth, so then there is a magnetic locking. So that's why proper combination, multiple number of combinations. So then we can get, this is also correct statements. So now what is the answer for this question? So only 2 and 3 statements are correct. Only 2 and, so this one is 1, 2 and 3. The following statements are correct with respect to 2. So 2 and 3 statements. And what is the answer for this question? 2 and 3, where is the 2 and 3? So option, the 2 is correct for this question. 2 and 3 statements are correct. Okay. And next one, let us solve question number 52. A 3-phase 4-pole 50H induction motor as a load rated speed is 1425 RPM, takes the 6 times of the block rotor condition. The started using the auto transformer starter with a 50% of normal voltage applied to the induction motors, and then the starting torque to the percentage of the rated torque. So same formula here, general formula, T starting by T full load is equal to the K square into S full load into I starting divided by the I full load whole square. Use this formula, you will get so the answer. So we required the ratio. So first the S full load is equal to, so per 3-phase 58 synchronous speed is equal to 1500 RPM. So 1500. So now this speed is equal to the air Ns minus N divided by Ns. the 1500 minus, okay, 1425, so divided by 1500. So now it is equal to 0.05, I think, 75 divided by 1500. So therefore this is equal to 0.05. Yeah, 0.05. And now substitute here this one, given that the current, starting current is equal to 6 times of the full load current. So starting current by full load current is equal to the 6. Now therefore starting torque by full load torque is equal to, the where transformation ratio is a 0.5 square and SFL is equal to 0.05 and this is equal to 6 square. So that is equal to 0.45. But in the percentage, so T starting is equal to, this one is the per unit value, multiplied by 100 you will get percentage, but 45% of, okay, TFL. So answer for this question, option so 3 is correct for this question. Okay. So this was the discussion about electrical machine questions which are from the transformer, induction machine, synchronous machine and also the DC machine. I hope you got it. Thank you very much.